Okay, so here is another example for class 13, and it also comes out of Munson's Fluid Mechanics. This is a 180 degree elbow. Water flows through it. It's a pipe bend. And the cross section area is 9,000 millimeters. Excuse me. And the flow velocity everywhere is 15 meters per second, so it's the same area all the way through. And the pressure at the entrance of it, so it's over here, is going to be 210 and 100. It's going to be 165 kilopascals at the outlets, right? So there's a pressure drop that goes across here, which is, it happens in pipes. I'm not sure that's quite a bit right there. So, but there's some viscous losses, is what we know. Calculate the horizontal X and Y components of the anchoring force needed to hold the bend in place. And they made the vertical axis Z, right? So we're going to look at it in the XY plane. So they gave us the area and they gave us the speed, so we can get the mass flow. That's probably a good thing to start with. So we can get that right here, and they say it's water, and we're using metric stuff. So that's 999 kilograms per cubic meter. They gave us the area as square millimeters. So that we would take, that's 1 million to get it into square meters, because that's 1,000 squared. And then we had times 15 right there. So what we end up with is 134.9 kilograms per second for a mass flow coming through there. Anything else I need before I go to the FBD? No. So I got my FBD and my, call it momentum diagram. And I'm going to draw this in the, let's see, there's Y and there's X. So this is going to be the Y-axis, and here's the X-axis. It just kind of makes sense looking. And we'll look down at this thing right there. And that's going to be equal to this diagram right here. It's like a big magnet. So I'm going to pretend the anchoring is going to take place right here. And I guess I'll go in the positive direction. So this is the RY, the reactions, and the RX. It just feels weird to make it in those directions, but okay. And it's coming in here and out there, so that's 1 and that's 2. So we'll say, here's the pressure. Okay, so remember this is a free body diagram, so we have sliced this thing off right there. So in doing so, internally to it, it's got a pressure that's acting on that face. It's also got a pressure acting on this face. So this is going to call this P1 times area 1, and this is P2 times area 2. And there are no other forces. So gravity's acting in the Z direction, and that's not in this plane. Over here, we have mass flow times velocity 1, and we also have mass flow times velocity 2 coming in there. Right away, by the way, we could actually just, from inspection, I think there should be a way to write that shortly, right? Can I go FI from inspection? So we're right away to say that. We could say that RX must be equal to 0, this guy, because there's no other forces. There's no other reason for there to anything. So they wanted it to the RX and Y components, but you don't need the X components because there's from inspection. By the way, I forgot to draw that arrow. There you go. So the equation that accompanies this free body diagram and momentum diagram is this right here. This is out, and we go minus beta m dot v in. All right, and that sign is because we do a dot, and the main equation this actually comes from, remember, we're doing a dot product between the velocity and the outward facing normal. So something coming in is the opposite velocity from the direction of that outward normal. Therefore, it makes a negative for the inlet and the outlet. So here's the pressures. Let's take a look in the positive y direction, which we could establish right there. So in the y direction, we say that we have P1A1 going to the right, P2A2 going to the right. I drew the RY, the reaction, to the right, just as by default I like to use the positive direction. Here is interesting though. We want to go to the outlet first. And so here is a problem that's different from some of the others. And that's the reason why I included this example. And hopefully you're going to look at this example problem when you're doing the homework so you could see something that's not intuitive. This says it's positive right here, but this is a vector. And we're breaking this down, even though we're only hitting things in the y direction. We have to remember that we're a vector. And that velocity at 2 is in the negative direction. Therefore, this is negative beta m dot v2. It's because the velocity is negative. Now this one over here, it's got a positive velocity, but it's negative right here because of this right here. It's because of this. This dot product right here has the velocity and the outward normal opposite from each other. They're dotted against there. Therefore, it's going to take, essentially, it's just the magnitude of this times the magnitude of this times the cosine of the angle between them, but the cosine is 180 degrees, and the cosine of 180 is negative. That's another way to think of those two things if you're taking a dot product, and that's why that's dot. So this is negative because of this velocity going in the left direction. This velocity is going to the right, but it has that sign. So this is a trap. It's a trap, as Admiral Akbar would like to tell you. So we have this pressure right here of P1 is going to be 210, but it's kilopascals, right? So that's 3. But then the area here, that's the 9,000 millimeters squared, but we need to divide it by a million. Same thing true here. We have 165 E3 because they're kilopascals, but also that 9,000 square millimeters. We have to divide that to get it into square meters. Here is our Y along for the ride. We're going to assume somewhere up here beta is approximately 1. We don't know, so this textbook from whence this comes. That's great name, whence. It doesn't use that momentum correction or whatever momentum flux correction factor, whatever the hell it's called. So they say 134.9, could call it 135, and velocity is 15, right? Velocity is 15 everywhere. Same thing over here. We have pretty much the identical thing. There's no reason why it isn't identical, but it's kind of interesting that they're both trying to fly off. So, but imagine this, right, for a second, all right? So say that we instantaneously cut this thing off right here. It's interesting that that's going to make this thing go flying that way. Well, think about it this way, right? If you cut it off right here and water was already flowing this way, it would go whoosh, flying off. If you cut here, flying off, this thing we call flying off, if you like this one right here. So that's sort of the ideas. This is the sort of like the dynamic thrust that's taking place onto this piece. So we're going to get an RY, and then these guys are turning negative too. So this pressure is also pushing here. So these are the actual physical forces, and these are sort of like the momentum parts of the thing. It's interesting, and this reaction is going to be a negative value of 7,421 newtons, or you could say that the RY is going to be 7.42 kilonewtons and posting the other way. And they did ask us about the RX. So there you go. And there's the solution to that one. We have one more to go. There's a lot of examples in this. hopefully someone will watch this and it'll be useful.